Hello, my name is Francisco El Val, and this is my real-world static analysis project presentation for the class MEC 1321 with Dr. Calvin Stewart. But before we get into it, I would like to talk about statics, mechanics, and why is it important for engineers to use all these concepts. So to begin with, what is mechanics and what is statics? Mechanics, as we already know, it's a branch of physics concerned with the behavior of physical bodies subject to a force or displacement, and statics is the study of rigid bodies at rest or at a constant velocity, which means that the acceleration on the object would be zero. And here's a picture of a truss bridge that I added, so you could see the design that goes into building things like that. So why do we use statics? We use statics in order to design and build structures. It gives us an idea about the dimensions we wanted to use, the materials we can use to build it, and the loads, the forces that are going to act on the structure. Because safety is our number one priority. So if there's a miscalculation, the structure could collapse and it would cause injuries or even deaths. Here are two design failures that I want to talk about. The first one would be of the Hyatt Regency Walkway. It was built for a hotel, Kansas City in Missouri, and on July 17th, 1981, they were holding a large party where a lot of people, of course, attended. Um, as you could see in the picture to the right-hand side here, these are the walkways, and a lot of people gathered on them. The supports, they were very weak, so the weight of all the people caused it to collapse, and sadly, it killed 114 people and injured 216 people. The second example that I want to talk about is of Galloping Gertie, which was a bridge that was located in Pierce County, Washington in 1940. This bridge was very famous in since it would swerve. People would like to drive on the bridge because so they could have a little thrill. And on November 17th, the bridge collapsed. There's no really an agreement of what actually caused it, but the speed of the wind was around 42 miles per hour. And these two examples caused a lot of rules to be added to construction. So for the walkway, they caused the bridges now to have the beams that would hold it, and for the bridges now they have to do the wind tunnel just in case that everything will be good and no harm would be caused to the people, and of course a lot of money since building all these structures costs a lot of money to the people that build them. So here are the steps to solving the problems. The first one would be to identify the knowns and unknowns. Second would be to draw a free body diagram and label it with what you already know. And the third step would be to solve by using the equations of equilibrium. So the structure that I decided to use for this project was a GECU plus sign that I have around my neighborhood. So here are the dimensions of the sign, the length, the width, and the height. And I did some research and I discovered that the highest wind speed recorded in El Paso, Texas was 84 miles per hour. So these are my knowns and unknowns. I have the dimensions of my sign right here, and I had to find the volume because this was very important because I needed to find the weight of the sign. So I assumed that the sign was made out of concrete. So I went to a website where I could find how much pounds there is in a cubic foot. So I found out that 150 pounds are in 1 cubic foot of concrete. So I did my equation and I found the pounds that I have, and then I use the conversions that I have on the right so I could turn it into newtons because I feel more comfortable working with newtons. And then I have the force of the wind, which was 84 miles per hour, and it's all distributed along the whole side. So I needed to turn it into one resultant force, which would be of newtons because I like working with newtons. So I used this equation here, which was this decimal times my miles per hour squared. So this is what I got for pounds per square foot. And then I used another equation that has the area that of the surface the force is gonna act on times the pounds per square foot times the drag that it's gonna have. So I have the pounds per square foot and I turn it into newtons per meter squared. So I went back to one of the problems that we have in our homework that was of distributed loads. And as you can see in the picture to the right here, this is the answer that I got. And then I had to turn my dimensions of feet into meters. So I had to do the pressure that I have times the thickness of the sign. So that's what I did, and that's how I got my newtons per meters. And then just to get my newtons, I had to multiply it for the length, which would be the x-axis, which would be on the x-axis. So this is what I got for my newtons. This is the free body diagram of my sign. There's no c-axis because there's nothing going on in the c-axis, and this leads me to use the classic x and y-axis. So right here we have the sign and we have the forces acting upon it. It's stuck to the ground, so there's going to be a force, which is a natural force, going upwards. The weight, of course, it's going downwards. The force of the wind's pushing it to the left, and then there's going to be a force of x pushing it to the right. And using the right hand rule, I was able to find that the moment was counterclockwise, and it was pointing towards us. So right here I have the actual free body diagram, which is the natural force, the weight, the f of x, and then the force of the wind, and then of course the moment going counterclockwise. So here are my equilibrium equations. So some of the forces on x, some of the forces in y, and then the sum of the moments. So for the forces of x, it has to be fx plus the force of the wind. So since the force of the wind is going to the left, right here in our axis that I have to the right, it means that it would be negative. So in order for the equation to all equal 0, the force of x should be equal and opposite to it. So this is how much newtons I have. For the forces in y, it was going to be the natural force plus the weight. So the weight's going downwards, so again it's negative. So in order for it to be 0 again, the natural force should be equal and opposite. So this is how much newtons I have. And for the moment, I had to go back to the question of the homework that we have a long time ago, which was similar to this one. And it has to be the length of it, which right here is 10.4 meters, had to be divided by 2 to find the center. So I divided it by 2, which gave me 5.2 meters. And then the moment would be the force times the distance. So this is the force of the wind that I have times the distance. So in total, the moment was this much newtons times meters. Here are the sources that I used for this project, and this concludes my presentation. Thank you.